calculate y prime and y biz, the second derivative, if 9x squared plus y squared equals 9. You might recognize this equation as the graph of an ellipse. So this is actually going to be an oval shape, an ellipse shape to be more accurate, of a graph. We cannot easily solve for y as a function of x, so we're going to use implicit differentiation here. Let's figure out the first derivative, d over dx of 9x squared plus y squared equals d over dx of 9. Now when we differentiate the left-hand side, the derivative of 9x squared is going to be 18x, because the derivative of x squared is 2x, and 2x times 9 is 18x. Plus the derivative of y squared with respect to x is going to be 2y times y prime. Got to use the chain rule, because y is a function of x. And then, of course, on the right-hand side, we get 0. Now, to get y prime alone, we subtract 18x from both sides. 2y times y prime is negative 18x. And if we divide both sides by 2y, we can actually reduce that fraction by 2, and we get negative 9x over y. So that is the first derivative of y. Now, if we want the second derivative, we can do the same thing. We can differentiate both sides with respect to x, and remember that y is a function of x. So to get the second derivative, we differentiate both sides. When we differentiate the left-hand side, that gives us the second derivative of y with respect to x. And then we have to differentiate the right-hand side with respect to x. Now, we're going to have to use the quotient rule here because we've got a quotient. And we're also going to have to use the chain rule when we're differentiating y, because y is a function of x. To make things a little bit easier, I'm going to pull out the negative 9. There's no need in actually including that in any of the quotient rule calculations. So this is negative 9 times the derivative with respect to x of x over y. So let's keep that negative 9 out front, and then let's use our mnemonic. We've got low d high minus high d low. Low is y times d high, the derivative of x is 1, minus high d low. The high function is x, and then the derivative of the low function, the derivative of y, is y prime, all over low squared. So it's going to be over y squared. So we can make this a little bit nicer. We've got negative 9 out front, and then this is really just y minus xy prime over y squared. This is one way to write the second derivative, but we don't want to leave it like this because we have the second derivative expressed in terms of the first derivative, and that's not nice. We just want this in terms of x and y. However, we do have the first derivative in terms of x and y, so we can take this and substitute it in for y prime down there. I'm going to rewrite this up here just so we have more room to work with it. And then we're going to do our substitution. All right, so when we substitute in for y prime, this is going to be negative 9 times y minus x times y prime, remember, is negative 9x over y. This is going to be negative 9x over y. This will all be over y squared. Now, these negatives are going to end up canceling out. Negative times a negative is a positive. So we've still got the negative 9 out front. This is going to be y, and then plus 9x squared over y, all over y squared. And then we don't love this y right here. We don't like to have a fraction within a fraction. So to get rid of that, we can multiply the top and bottom by the LCD of the fractions inside the bigger fraction. We can multiply them by y. Basically, that's going to get rid of that y. When we do that, again, we keep the negative 9 out front. When we take this y and distribute it up here, y times y is y squared. And then in the other term, the y's cancel, giving us 9x squared. And then in the denominator, y squared times y is going to be y cubed. So that is good. And we could leave it like that, but there's a really interesting thing here that I absolutely love. I love this problem. If we look at the numerator here, y squared plus 9x squared, and we look at the original problem, we know that y squared plus 9x squared is just equal to 9. So this whole thing that I've just highlighted is actually equal to 9. So we can rewrite this as negative 9 times 9 over y cubed. And that is the same as negative 81 over y cubed. And so our second derivative is just equal to negative 81 over y cubed. That is so much simpler and more beautiful than all of the other things that came before it in this problem. So yeah, that's just a really beautiful second derivative.